In the previous video, I got the Flex operating system up and running on the Altair 680 computer that you see here on the top. And instead of using a floppy disk controller and disk drives, I exchanged the floppy data through a serial board in this computer to and from a server running on a PC. And then later I also demonstrated a server running on a little Raspberry Pi as another option. And this had to be done because there was never a floppy disk controller or a disk system of any sort made for this Altair 680. So this is just one of the very few ways you could possibly have ever run a disk operating system on this Altair 680. Now, since I made that video, a number of you have asked whether or not something similar could be done with the Southwest Technical 6800 computer that you see here on the bottom. Now, of course, Flex was developed for this for the Southwest Technical 6800, so there's definitely a floppy disk controller and a disk system available for this computer. However, if you didn't happen to have that controller or you don't want to mess with floppy disk drives, then running this through a serial board like we did with the 680 might be something that was of benefit or interest to you. And that's what we're going to take a look at in this video today. I have this 6800 computer configured to run Flex through a serial port instead of going through a disk controller. Let's take a look inside, see how this is configured. Back here in the I/O bus, you can see I don't have slot 6 populated with the disk controller. That's normally where that would go. Back here, I now have two serial boards. One in I/O slot 1 is the normal serial board used for a console with anything you would do on the Southwest Technical. And then I have another serial board in I/O slot 2. That has become our interface to the disk server. Now these two boards look completely different. However, this little blue board is a modern drop-in equivalent for the original MPS serial board. The advantage it gives you is it has a nice little 9-pin connector that's easier than using the original Molex connector. This one also does a bit better at the higher speeds I'd like to run this at. I got this board working pretty reliably, the original, so it is doable. But you probably don't have two of these boards anyway, so if you end up purchasing one, I put a link to where you can buy a modern drop-in equivalent like that to make your life a little easier than trying to coax the original one into doing the high speed. All right, so if previously you had run Flex in your computer, then at this point, this configuration would run Flex through the serial port. However, it would be miserably slow. And that's because the baud rates in this computer were only 110 through 1200, and we want to run something much, much faster. What's interesting about this computer is the baud rates were not generated on these serial boards. Instead, they were generated back on the CPU board and actually ended up in the bus. I don't know if you can read these here, but there's 5 baud rate lines right here on 5 of these pins, again, from 110 up through 1200 baud. But what we'd like to do is generate a much higher baud rate. And since those come from the CPU, let's take a look at this CPU board and see how that can be done. All right, so this chip right here is the baud rate generator. Here's the crystal for that chip. It outputs, I believe, 15 different baud rates, all simultaneously on it. And some of those are run, actually 5 of them are run through this chip, which then buffers them onto the bus for use by the other peripherals in the 6800. So all we have to do is disconnect the ones that we'll probably never use and instead connect the higher baud rate that we want. So you can see here I've pulled pin 5 out of its socket. This is the 600 baud line. I'll never use 600 baud. And then on the back of this, we've got the jumper wire coming from pin 18 to that pin 6. On pin 18 is 57.6K, so a very high baud rate compared to the 1200 or 600. It now connects over here to pin 5. Therefore, it is now being placed on the bus on that 600 baud line. So I've got 57.6 out there on those serial interface boards. If I want that baud rate, I just choose the 600 baud position, and now I've got 57.6. Now, if you look at this, you can also see there's another jumper on here. This particular one puts 9600 baud on the 150 baud line. And that had nothing to do with this project in particular. In fact, it might have already been done on your computer, or you might have already done it, because it's nice to have 9600 baud for terminals. And that's by lifting pin 8, which was the 150 baud line. Now we've put 9600 baud on that. So again, not required for this project, but it's nice to have a 9600 baud. Anyway, so we have got the 56.8 we need. And with that baud rate, this is actually faster than the original Flex system was in their MF68 enclosure using SA400 drives. All right, so we got that all set. At this point, the only thing left to do is make sure the rest of the hardware is ready to operate Flex. Now, if you have ever run Flex on your computer in the past, then most likely it's ready to run and you can just now move on to the software, which we'll discuss next. But if you've never run Flex on your machine, then there are some mods that had to be done in order to make it run Flex. And these are the very same mods that were described back in 1977 by Southwest Technical. And I put a link to those mods in the description of this video so you can see what would have to be done. So obviously the next step is now to get a version of Flex for this Southwest Technical 6800 computer that is also compatible with the serial disk interface we're going to use. Get that built up, loaded and running so that we can then create a bootable disk. Now, this process and virtually all the code is identical to what we did for the Altair 680 in the previous video. So rather than rehash this in detail all over again, I'm going to refer you to that Altair 680 video if you want to see the details of how this is all done. I've put a link to that video in the description of the one you're watching now. All right, so as we saw before, to create the memory resident portion of Flex, it requires 3 files. One is this Flex core file. This is a binary file provided on the disk if you need it. I've downloaded that and converted that binary image to an SRecord file so I can use it here on the PC. 2 other files are a console driver and then a disk driver to handle what's unique about your machine versus any other machine. Now they provide samples of the console driver and disk drivers with Flex. And the console driver, the image or the sample they provide is for a Southwest Technical computer. So this file, frankly, is ready to go exactly as is. I can just use the sample file for my 6800 machine. So that part's done. The disk driver, I'm going to use the exact same disk driver I used on the Altair 680. The only thing I have to change is the address of where the 6850 UART is on that serial port. It was at F6 or F1006. Now it's at 8008 and 9 here for the Southwest Technical machine. At that point, I have the files I need. So I've assembled those, which gave me SRecord files for the console and disk drivers, and I have the core file. At this point, I can load this into the Southwest Technical and run our version of Flex. So let me bring up that terminal here, turn on the machine. All right, that $sign is the prompt from SWTPC. That's the ROM monitor in the 6800. The load command is like it was in the Altair 680. It's expecting SRecord files to come in through the console serial port, either from a teletype or the way they did their cassette interface. The cassette interface actually came through the console port as well. On this terminal emulator, I can just send the file, and it looks just like what SWTPC expected from paper tape or cassette. All right, the core file is in. Let's load the console driver. And let's load the disk driver. And at this point, we'll have the memory image of Flex ready to go. The entry address of that is at AD00. This was just like we booted it. So it is now the new year. All right, and there is the prompt from Flex. So we were able to load Flex into RAM and start it all up. Now, as you know, a lot of Flex is on the disk itself. All the commands you run are disk-based commands. So what I've done is I've loaded a Flex image here that is a single-sided, single-density disk, which is the format that the serial Flex system is compatible with. This is a disk image I use all the time on a real floppy controller and real disk drives. But again, it's completely compatible here. We can see everything that's on that. It's just that it's not bootable. Here is the memory image of Flex for what's out on this disk. This expects the real disk controller and the real floppy drives. So all we have to do is create our own system file like this. We called it serial Flex in that previous video to make this disk bootable and have it boot serial Flex instead of this flex.sys. All right, so the procedure for doing all that was to combine the flex.core file, you can see that's right here, with the console driver file. I uploaded the source of it and assembled it here, so I have the binary for that. Also with the disk driver file. I uploaded the source and assembled it, and I have the binary for that. So at this point, we combine those 3 things with the append command. So here is the part of Flex that doesn't change. Combine that with the disk driver, and combine that with the console driver, and we'll write that out to something called serialflex.sys. And at this point, it's identical to this flex.sys that you see right there, except that it's the correct one for our serial flex system. Hopefully there we go. All right, so now if you look, we've got serial flex out here on the disk. Now, how do we make the disk boot that? Well, when you boot a disk, for example, starting with SWTBug, there's a D command in the SWTBug ROM monitor that boots the disk. It goes out to the disk and reads sector 0 off of track 0. And in sector 0, track 0, Flex expects a loader to be present that's going to actually load Flex into memory. And it will load whatever you say, for example, flex.sys or serflex.sys. So right now that bootloader is the one for a real disk. We need to put the one for our serial disk out there. Now I'm going to use the exact same routine that I used on the Altair 680. Except again, I'm just going to change the two equates to be for where the serial port is on this machine. All right, so that is this flex load routine right there. And I've already assembled it to be flexload.bin. Now Flex provides a command to put this out onto the disk called put loader. To do that, first you load the loader into memory. This is going to put it where it executes, which is at A100, but it's not going to actually run it. So now it's in memory. Now put loader will take whatever's at A100 and write it out to sector 0, track 0. And it says, is in the correct drive? Yes, it is. So now that is out there. So now the right loader is on the disk. However, it does not know what operating system to load. We want it to point to serflex.sys. So there's a standard command in Flex called link that points the bootloader to whatever actual system file you want to load. So it goes to the directory, finds out the track and sector this starts on, and then patches it into the bootloader down on sector 0, track 0. At this point, this disk is bootable. I can go back here to the monitor and I should be able to boot it. Well, how do I do that? I don't have a ROM monitor that knows how to load a track 0, sector 0 off of the disk. Instead, the D command expects the real disk drive. So for now, until I make a ROM boot of my own, I'm going to have to use the same routine I used over in the Altair 680, and that's this RAM boot. This is essentially what you would put into a PROM to boot it. This is going to do nothing but go out to sector 0, track 0, load it into memory, and jump to it. Same routine I used on the Altair 680. The only difference is I had to change, again, the address of the 6850 of the UART in the serial board. At this point, this is ready to go. With this SWTBug, most things you load set up a go register at A048, so I can just hit G for go, and it's over here booting, and we're up and running. All right, so I now have a bootable disk, and you could just leave it this way, play with it. Anytime you want to, just manually load that ROM loader as a RAM version into memory and jump to it and run Flex. And you can load most any images you want into these other disks, and they will all work, even though they're not bootable. The data portions are all just fine for use with this. All right, I'm going to go ahead now and do a quick demonstration where I use a standalone disk server and actually have the boot command in ROM, so you could see what it would be like if you really cleaned this up and made it a standalone solution. All right, to wrap up this video, I'm going to go ahead and do a very quick demonstration to show you how autonomous this system could really be. Pretty much the same as just having a couple of external floppy drives hooked up to it. You don't have to connect to a PC to get your server function. Towards the end of the last video, I demonstrated a server on a little Raspberry Pi, for example. Now, the downside of the Raspberry Pi, you are going to have to get on a PC and log into that Pi to then start up the server. And then when you're done for the day, you're going to want to log back into it and do an orderly shutdown of Linux to make sure the file system isn't corrupted. But what another hobbyist has done is made this little server that you see here. This is using a little ESP32 Arduino-like processor on top, and he made this board it plugs into that gives us connections over to the serial port that you're using for the disk operations. It also has a SD card on it to hold disk images. He has a number of commands to allow you to load and save and change disk images. But one thing that's important is it doesn't use any sort of formal operating system. So you turn that thing on, it's instantly ready to go. When you're done, you just turn it off. And when you do turn it on, it automatically starts up whatever was in the disk when you last used it. So you don't have to hook to a PC to continue doing what you were doing. You have 4 disks loaded in there, for example. That's a lot of activity and different things you could work on without really needing to swap disks at all. All right, now to boot this, let's go ahead and reset the computer. There's our swap bug prompt. If you had real disk drives, you would just turn this on and hit D to boot. Now, can't do that. You saw me have to load a loader into RAM, so how am I going to get around that? Well, what I've actually done is augmented the swap bug in my system to allow the D command to boot from this serial drive as well. And in fact, my swap bug had already been augmented to boot from 2 or 3 other hardware devices that I occasionally use. So adding this in my case is no big deal. But this is one option. So now I just come in, I do a D to boot. It sees that there's no other controllers in there, so it uses the serial port. And we're up and running just like these drives were just always there. Not having to do anything special, not having to hook to a PC, not having to log in and do anything unusual. Here's the content of the 2 disks we're using right now. We have basic and some basic work disks and things I've shown you all before. So Flex is up and running, that simple, and a nice autonomous system without any PC involved whatsoever. All right, well that does it for this video. Not sure what's going to happen next, but somebody always asks a question and ends up turning into an interesting project.